Hello there, welcome back to the Differential Questions by Alexander. Okay, so today we're going to talk about the Laplace Transform, and then this is something that we will use to change a differential equation. We're going to use this Laplace Transform to change the differential equation into an algebra equation. So that is a new technique to solve differential equations by changing the calculus into an algebra, and hopefully we can solve the algebra, and then we'll get eventually the answer to the differential equation. But before we start doing this differential equation business, we actually want to know what is the Laplace transform. And so what I'm going to do is I'm going to give you one explanation of what the Laplace transform is, and I'm going to do that by using a little bit of calculus. Okay, so there's many ways to talk about the Laplace transform, but just to build up on what you already know, we'll start with the calculus. Okay, so suppose that you have this question back from calculus 2, and here a is a number, so it's just a fixed number. And then in calculus 2, you have this indefinite integral. It's indefinite because you have this infinity on the integral. And so you have to kind of figure out how to integrate this. And so the first thing that you have to do is you have to change the infinity into a finite number. So this is the integral from 0 to b of the same function. So right now, this is just a review of calculus 2. And so you would integrate this, and you actually have to do a UV substitution here. So integration by parts, or you call it the UV substitution. And then after you do that, you actually make another UV substitution. And so what I've done here is I want to just show you what the work is that you will have done in calculus 2. And so this is what you will have done. And you get the answer at the end of the day to be this thing here. Okay, so 1 over a squared plus 1. And what I want to focus on is this. So the original integral is this thing on the box, which I'll put here on the very bottom also. And what I want to focus on is the following. Okay. So in calculus 2, you could say the following. You have this blue function, the function in the blue box, and then you put it into the integral, the sine function, and you integrate in this specific way, and out comes out this red function, or the function in the red box. Okay. So the way that I want to think about it is the following. I'm going to change the problem a little bit. Okay, so the answer to this guy was, again, let me write it down. This is 1 over s squared plus 1. And what I want to do now is I'm going to change the notation a little bit. So this is a problem that you had seen in calculus 2 or could have seen in calc 2. And so you do the integration and you get this to be your answer in red. And you're done. Oh, so this is not an S, this is an A. And so what we're going to do now is we're going to change the parameter. The name of the parameter originally was A, and then we're now going to change that into an S parameter. And not only that, we're also going to, instead of saying that we are integrating with respect to the X variable, we're going to integrate with respect to the T variable. So we have the same question, except that we're just changing the notation a little bit. And again, we have this function, which is the sine function in the blue box. You put it into this integral, which is a calculus 2 integral now. And now the answer to this integration, after you do all the lengthy work, the answer to this was 1 over s squared plus 1, for this specific example. Okay, and so what I want to say is the following. Notice that this thing is actually a function of the variable s. Okay, so the output after doing the calculus 2 calculation, you get this function, which is the red function, and then it's the 1 over s squared plus 2. So there's two things here. One, you have to realize that this is a function, and two, you have to realize that this is a function of the variable s. In the very beginning, the thing that you put into the black box was the sine function. So the original function was f of t is equal to sine of t. And so what I want to focus on is that the blue function is in the variable t, and you plug it into your black box, which is your calculus 2 integration, and then the output is your red function, which is 1 over s squared plus 1, and this is a function of the variable s. And so the way that I visualize the Laplace transform is that the Laplace transform is the black box that allows you to plug in a blue function into black box, and then the output is the red function, which is called the Laplace transform of the blue function. So the red function is the Laplace transform of the blue function. Okay, but the black box is your machinery. Okay, so that's how I think about the Laplace transform. It's a way to change the blue function into the red function. Now, I want to make this a little bit more formal, so I'll just repeat what I just said. And So just to kind of make the picture a little bit more clear, again, the f function is the function in blue, which is sine of t, and this is a function of the variable t. You put it into your black box, which is this calculus 2 integral. You put the sine function into the black box, and so that's where the sine is. And now you do the calculus 2 integration, and then the output of this, we said that the output was equal to, in this specific example, this is 1 over s squared plus 1. And so this is your output. And so what we say is that the red function is the Laplace transform of the blue function. We change the blue function into the red, or that the capital F is the Laplace transform of the little f function. All right, so that's the result for the specific function sine of t. And for the part B, what I want to do, I want to graph the functions. So notice that the f function is in the t. Let's just say that this is the ty axis. And notice that if you had 2 pi here, then your blue function would be something like this. Okay. So that's your sine function, but then this repeats forever. So this repeats, the pattern repeats. So that's the graph of the f function. That's the graph of the f function. That's in the ty plane. And now the capital F is not in the ty plane. It's going to be in the sy plane. And now we want to graph the red function. And if you either get a calculator or do this by hand, then your graph will look something like this, look like a little mountain. And the peak is at 0. Okay, so that's what the graph of capital F is. And so what the Laplace transform does is that it transforms or changes the blue function into the red function. So the blue function is in the t variable. The capital F function, the red function, that's in the s variable. And so that's how I visualize the Laplace transform to be. It's a method to change the blue function to the red function. But you have to be careful that, so in the beginning, it's the t variable that you are dealing with, and then on the end result is the s variable. All right, so we can make this a little bit more general. We don't have to just put in the sine t function. We can also put in sine of other functions. So here, just to make it a little bit more formal, f could be any function. At least at the moment, we are saying that f could be any other function, and then we put it into the black box. So put it in there, and then you multiply by this e to the negative st, and then you do the integration. So do the calculus 2 integration, and then the end result, after you do the calculation, you get this function which will be in red. So some formula, and the formula will be in the variable s. Okay, and that is the Laplace transform. The red is the Laplace transform of the blue little function. But now there's a catch here. The catch is that this integral has to converge. Remember that this integral is an indefinite integral, which means that not all the time would you get this integral to give you a function. It won't be a function all the time. So there are a few restrictions to the little f that you can plug into the Laplace transform. Okay. So before I move on, I want to also change the notation a little bit. So sometimes we do write down this capital F because the little f was the input, and then the output is the capital F. So little f is the input, capital F is the output of the Laplace transform. And we also say that the capital F is the Laplace transform of the little f. Now, there's another notation that we also use, and the notation is given by here on the bottom. So the input is the little f function, and so we use this notation to say that the Laplace transform, you put it into the black box, and so that's what this notation here says. So you put in the blue function into the Laplace transform and do the calculus, and then the output is going to give you the Laplace transform. So we say that Laplace transform of a little function f, this is going to be equal to your formula. So this is the same thing as saying that this is the f of s. Okay. So different notation for the same thing. We're saying that these two things are denoting the same thing. Okay. We're saying that the capital F of s, that's one notation, and then the fancy L with the curly bracket f of t, that is, they mean the same thing. All right. And the second one is preferred because we want to think this as being an operator. And we talked about operators before. We previously talked about the differential operators, but that's a different story. All right, so now what I want to do now is I want to go back to the sine function, And previously we dealt with the sign when the n was equal to 1. But now there's a theorem, you do the calculation. So this is actually calculus 2 here. If you do the calculation, then the Laplace transform of the sine function will be given by this formula. Okay. So if you input the sine of nt, or whatever n you want to choose or want to put in there, then the output is going to be given by this red function. And so this is a little bit more general than the first example that we dealt with. So I'm giving you a formula here, and so we want to memorize at the end of the chapter. We are going to have a list of tables, a table that gives us a list of the different Laplace transform of some basic functions. So the sine function, the cosine function, t to some power, and then e to some exponential at. All right, so here with this example, I want to say a little bit more. Okay, so remember that we have this blue function, we apply the Laplace transform, and then we get this red function. Okay, we get the red function, and so we could graph them. Okay, so we could graph them, and so suppose that we graph the f function, and so this is the t-axis, and so depending on the value for n, so here's the 2 pi, and then depending on the n, so suppose that you have n is equal to 2. That means that you will have 2 copies of the sine function in that interval. So you will have something like this. That's 1 copy. And then 2 copies on the interval to 2 pi. But then you repeat this forever going to the right side. So that's the graph of the f function. And now when you graph the Laplace transform, again, this is for n is equal to 2, then your graph will look something like this. So it will look like a mountain. And this is the s variable. Okay, so this is the s variable, and technically we should only be drawing the second half here. Okay, so this is what the graph is, but we visualize the whole thing. So now the question is, what happens as the n gets bigger? Okay, what happens as the n gets bigger? So let me try to draw this on top of the picture that I already have. So you suppose that you have n is equal to 3 now. So what that means is that you now have, on the interval between 0 and 2 pi, you now have 3 copies of sine. So 1, 2, 3 copies of sine on the interval 0 to 2 pi, and then the pattern continues on. So you have more waves to the f function. So that's the function in purple. The function f in purple is when the n is equal to 3 on your sine function. And so what does that do to the Laplace transform? So if you do the calculation, you roughly will get the following. And let me see if I can put this in a different color. You'll get something that looks roughly the same thing, but it's going to be a little bit more flat. Okay. So the yellow, so yellow is the n is equal to 3 in the Laplace transform. So it's good to go back and forth. You have the original function f, which is in the t variable, and then you have the Laplace transform, which is in the s variable. And then you, depending on what your function is, you want to know what happens if you change the little f function by a little bit, what happens to the Laplace transform. But that's going to be a different story later on. And so now what I want to do now is I want to talk about the Laplace transform more generally. So there's 2 properties that I want to say about the Laplace transform. Technically, it's only 1 property, but I break it up into 2 parts. So one property of the Laplace transform says that if you want to take the Laplace transform of 2 functions, then this is actually the same thing as taking the Laplace transform. And I'll just write down L because it's hard to draw the fancy L. So the Laplace transform of the f function plus the Laplace transform of the g function. So you can actually break up the Laplace transform if you have a plus sign. And the same thing is true if you have a minus sign. So if you have a minus sign, then you can just split up the Laplace transform of the first function f minus the Laplace transform of the second function. Now, if you have a number a multiplied by the function, then you can actually factor out the number a out of the Laplace transform, and then you just calculate the Laplace transform of the f. So this is our 2 properties that we're going to use to be able to calculate more complicated functions. So let me just give you an example here. So we're going to use this extra piece of information. So this is technically a theorem here. So Laplace transform of t to any power is given by this formula. And so now the question is asking us to find the Laplace transform of the summation of these 2 different functions. And so what we can do is, so we're going to write down 7t squared plus the Laplace transform of 8 sine 4t. So that's using the first property of the Laplace transform that is linear, so you can actually split up the Laplace transform into the Laplace transform of two pieces. You can also factor out the 7, so this is the same thing as 7 Laplace transform of t to the second power plus 8 Laplace transform of sine of 4t. So I should be writing down the fancy L and then the fancy curly brackets, but just I want to keep the notation as clean as possible. So now we are going to use the formula that we have on the top to calculate the first Laplace transform. So according to that formula, this is going to be equal to, and then we're going to multiply by 2 factorial divided by s2 plus 1. I want to show my steps. And now this is 8 multiplied by the Laplace transform of sine of 4t. And do you remember what the Laplace of the sine nt is equal to? So this is going to be equal to 4 divided by s squared plus 16. So that's using this formula that we introduced earlier. So now we just simplify the notation. And so 2 factorial, so let me just write it out this way. So this is the same thing as 2 over s to the third, and then plus 8, and then 4 divided by s squared plus 16. And yes, you can simplify this a little bit more, but I just want to emphasize that we are using the linear property of the Laplace transform to calculate this original Laplace transform of the original blue function. So Laplace transform of the original blue function is given by this end result at the very bottom. So right now we are changing a function in the t variable. We are changing it to a function in the s variable. Okay, and we're going to use this Laplace transform later on to change a differential equation, which is a calculus equation, and we're going to change that equation into an algebra equation. So that's our goal. But right now we just want to get comfortable with the Laplace transform. All right, so far the story has been good, but now there's one thing that we have to go back to the question about the Laplace transform being an integral, an indefinite integral. So this function, if we put in the e to the t square function into the Laplace transform formula, then this is going to be undefined. Okay, so that means that the integral does not exist. Okay. And so this is not a good thing for our story. So what we're saying here is that not every function can you plug into the Laplace transform. So not every function can you just stick it into the Laplace transform and say, oh, I'm going to figure out what this is. So that means that we have to be a little bit more careful on what functions we can plug in. And so the question is, what conditions do we need on the f so that the Laplace transform does exist? So that's the discussion that we have next. So the first part of the answer to the question is this: we need the function f to be piecewise continuous. So what piecewise continuous means that the function f only has finitely many jump discontinuities. Okay. So another way to say the same thing, but just in different words, is no infinite discontinuities and only finitely many components. And so what I've done here on the bottom, I've listed down 3 functions that are not good examples. So those are the f, g, and h on the very bottom are bad examples, or examples that do not satisfy, that cannot be classified as piecewise continuous. So let me just draw them, that way you have them in mind. So the first function, this is the graph of this will look something like this. Okay, so this is y equal to 10. And then this is equal to y to x is equal to 4, and then your graph of the function looks something like this. And so it looks like this. And so the blue solid part, that's the graph of the function. And so what do you notice about this blue function? Okay, so we said that we do not want infinite discontinuity. So you have this infinite discontinuity. So that's a bad thing. So infinite discontinuity. So this means that this blue function cannot be plugged into the Laplace transform. So this is an example of a bad function. So let me just actually make that very clear. So these are bad functions. The f, g, and h are bad functions, but for different reasons. Okay. So the f function is a bad function because you have an infinite discontinuities. So we don't want infinite discontinuities. Now for the second function, this is a function that you might not have seen previously. So this is called the floor function, the thing on the things that look at square brackets. And so the idea of this floor function is roughly like this. So you break it up into pieces, And so the graph looks like this. And so so it looks like stairs, or they like a like a saw, like a sawtooth. Okay. And so this pattern continues on forever. So this is what my dot represents. The pattern repeats forever. And so what we are saying here is that we only want finitely many components. Okay, only finitely many components. And so what this g function has, this one has infinitely many components. Okay, so that's so infinite components, or infinite number of pieces to the graph. So that's why the g function is a bad function. Okay, so don't worry about the formula, the t minus the square bracket looking thing t. The more important part is about the picture. The picture here is that you have a graph that has infinitely many components, or infinitely many pieces to the graph, and so this is not a good function for our purposes for the Laplacian form. So that's a bad function for us. So now the last example is going to be something that you've seen before. So the tangent function, so this is tangent of t, and you have to remember that the tangent function, usually you only draw one branch of the graph, and so the branch that you see roughly is like this. So it goes like this, but you have to remember that the actual graph is actually repeated infinitely many times. So you repeat this blue graph of the tangent function infinitely many times, and so now, so you have infinitely many components for the tangent function, and then you have infinite discontinuities on the graph. And so that's why this tangent function is not a good function for the Laplacian form, because it's bad in both ways. It has infinitely many pieces, and it has infinite discontinuities. All right, so this is just to give you an idea of what piecewise continuous means. And so that's my rough definition, or my rough explanation of what piecewise continuous are. And so if we were to draw a picture of a piecewise continuous function, then your graph might have, like, let's say 3 pieces. And so your graph might look something like this. You might have one piece here, another piece there, and then another piece right there. So 3 pieces, and then you don't have any infinite discontinuities. You just have jump discontinuities. So the graph on the very top, that is a good example of a piecewise continuous function, which is a good function for us for the purpose of the Laplace transform. All right, so now the next condition that we need to have for the f functions is the following. So this is something called the exponential order. We want the f to be of exponential order, and so my explanation is going to be the following. You have an inequality here, but my explanation is going to be with picture, and then so roughly this is what the picture is saying, or what the definition is saying. You have this exponential function, so this is me to the ct, and this is me to the negative me to the ct. Okay. And so what the definition is saying is the following. For the function to be of an exponential order with these specific values, the m and the c and the t, then that means that as you go to infinity in the t-axis, your graph stays below, okay, below the exponential function, or above the exponential function if you're on the bottom parts. So a bad example would be something that the red function. So the red function will be a bad example of an f function, because the red function is much bigger than the exponential function that we have. Okay. So that's roughly the idea about exponential order. It's a little bit more detailed, but I just want to kind of give you a rough idea of what the inequality is saying. The inequality is saying is that as you move forward in the t variable, the graph of the f function, the graph of the f function that you care about should be below the exponential function with specific values for m and specific values for c. So that's roughly the idea. And then one way to say this is that the function does not get too big too fast. All right. So the theorem that we have is, if you have those two conditions to be met for the f function, so if f is piecewise continuous and is of exponential order, then the Laplace transform exists. Okay. So the Laplace transform, if you plug in that specific function into the Laplace transform, then the Laplace transform will be a good thing. It will give you an actual function. Okay. So we have to check those two things before we can actually calculate the Laplace transform. So here I'm going to give you two examples. The first one I'm going to calculate the whole thing out, and then the second one I'll just set up the integral. So question 5 is asking us, here is a function. It's a piecewise function because we have three pieces to it, and then we want to find the Laplace transform of this f function. But before we can find the Laplace transform, we should say should we calculate the Laplace transform, meaning is the function f, is it piecewise continuous, and is it also of exponential order? Okay, so let's just draw the graph really quick. So the graph of this looks something like this. So this is the t-axis, and it's broken up into a, b, so 0, a, b. And then on the first piece of the graph, and I'll put this in blue. So between 0 and a, the y value of the function is 0. So between 0 and a, the function formula is telling you that the function value is equal to 0. So that's why you have this solid line there. Now between a and b, the function value is equal to k, and k is just some positive number, and so we'll just put a solid line there, and the y value of that is k. So that's the second piece of the graph. Now the third piece of the graph tells you that for t bigger than b, the y value is equal to 0 again, and so that means that the function is 0 here afterwards. Okay. So now looking at the graph, just looking at the graph, we can see that the function has only three pieces, so that's good. And not only that, each piece only has a jump discontinuity. It is true that we have open circle here on the b part, and that's perfectly fine. We never said that we had to have the function defined on all the points. So, but the discontinuity is a jump discontinuity at a and also at b, and it only has finally many pieces. So the function f that we have is piecewise continuous. Okay. So f is piecewise continuous. Now, what is the other thing that we have to check? We have to check that the function does not get big, like in the y value. We have to check that the y values of the function do not get too big, too fast as you go forward in t variable. And in this example, the function is actually 0 after b, and so obviously the function does not get big too fast. So f is of exponential order. So just kind of think of this as exponential order, saying that the function does not get big too fast. And in this case, the function is actually 0 as you go forward in t. All right, so that means that we can calculate the Laplace transform of the blue function. And so now that's what I'm going to do on the next slide. Okay, so I'm going to erase this. This is just to check that we can go ahead and calculate the Laplace transform. And so let's calculate the Laplace transform. And this is, oops, let me go back. So you have to recall that the Laplace transform is an integral. This is an integral from 0 to infinity of the f function e to the negative st, and we are going to integrate with respect to t. Now, since this is a piecewise function, we're going to break up the integral into pieces. So this is going to be the integral from 0 to 1, and then between 0, not 0, 1, 0a, between 0 and a, the y value of the function is equal to 0. So this is 0 times e to the negative st dt. Now, this is going to be the integral from a to b. So now we're looking at the second piece of the function. And on the second piece of the function, the y value is equal to k. So we're going to put in k for the f, and this is going to be e to the negative st dt. And now we're going to put in our last integral, which is from b to infinity. And now for that last integral for t between b and infinity, the y value is equal to 0 again. So 0 times e to the negative st dt. And so the first integral and the last integral, they go away because 0 times anything is 0, so that goes away. And so that means that you only have to focus on the middle integral. And if you were to integrate that, so integrate the middle integral, notice that k is just a number. And so if you integrate this, you will get the following. So you get k e to the negative st. And since we're integrating with respect to the t variable, we divide by negative s. And then this is going to be evaluated from t is equal to a and t is equal to b. And so in this case, this gives you k negative s, and then we're going to plug in the top minus bottom. So this gives you e to the negative sb minus e to the negative sa. And yes, you can simplify that a little bit if you wanted to, but notice that the s variable appears in the formula, and you have to be careful here. And so what we're saying is this is our Laplace transform The function in the red box, that is the Laplace transform of the original blue function. And the original blue function was given to us as a piecewise function. And so this is how you calculate the Laplace transform of a piecewise function. So that's one example. Now for the second example, we are going to just only set up the integral just to make sure that we are comfortable with the integration, with the setup. So, but before we do that, again, we want to draw the function to see that we can actually apply the Laplace transform. So again, this is the t variable, and just call it the y variable. And now this is broken up between 0 and 1. And now between 0 and 1, the graph of the function is t. So let me just draw that in blue. So this is increases as a line. So between 0 and 1, you have that. And now from 1 forward, so in t between 1 and infinity, the y value is equal to 2. And so that means that you have this straight line, and that is at the height of y is equal to 2. And that is the graph of the function f. So this function f is a piecewise function. How many pieces does it have? It has only 2 pieces. You can actually count them. It has 2. You can actually count them with your hand. Now the other thing that we have to check is that this function is that this function only has a jump discontinuity. So this has a jump discontinuity, and it only has finitely many pieces. So that's good. So it is piecewise continuous. Now the other thing is that this function stays flat at 2 as you go forward in the t direction. So as you go forward in the t variable, then the function stays flat. Okay, so it does not get big too fast as you go forward in time. So that's a good thing. So that means that the function is also of exponential order. So that means that you can actually calculate the Laplace transform of the blue function. So that's what we're going to do, or at least we're going to set up the Laplace transform. So let's start the setup here. And so we need to write down the following. This is going to be the integral from 0 to infinity of the function f of t e to the negative st dt. And now this is going to be broken up into 2 pieces, the integral from 0 to 1. And then between 0 and 1, the formula of the function is t. So that's what we put in for the f function. So this is going to be multiplied by e to the negative st dt. And then we're going to write down our integral from 1 to infinity. And then between 1 and infinity, the y value, or the function value, is equal to 2. And so this is going to be 2 times e to the negative st dt. And so that is how we set up the integral here. Okay, so that's how we set up the integral for the Laplace transform. And now for the first integral, I'll just give you a little hint here. You have to do a little bit of a u substitution here, not too difficult, but you have to do a uv substitution. And then for the second integral, you have to take care, technically you have to take care of the infinity, but I know that there's some shortcuts that you can do, and then they work. So whatever you do, you can integrate this by calculus 1, technically. And so at the end of the day, you get your formula for the Laplace transform. Okay? So at the end of the day, you do the integration, which is calculus 1, calculus 2, and you get your formula, and then that is going to be the Laplace transform of the original blue function, which I'll put here on the top. So Laplace transform of the blue function, which is a piecewise function, is the formula that you get in red. All right, so just 2 examples with the piecewise functions, and I also give you some the Laplace transform of the sine function, and I also give you the Laplace transform of the t to the power n function. So I hope that this explains what the Laplace transform does a little bit. And remember, our goal is to change a differential equation into an algebra equation. But before we do that, we need to be comfortable with what the Laplace transform does. And my way of thinking it is that the Laplace transform changes a function, a blue function f, and changes it into a red function, capital F. And the original function is in blue is in the t variable. The new function in red is in the s variable. So just keep that in mind. And then on the next video, we'll talk about the inverse Laplace transform. And then with that, we'll be able to talk about the solving a differential equation. All right, I hope that this is helpful, and I'll see you next time. Thank you for watching.